So, thank you a lot for the invitation. First of all, to Andrei, I'm very happy to be here. It's the second time I'm in this beautiful place, and in the future I hope to stay here many more times during the year. So I really hope to establish several scientific collaboration with all of you. Under suggestion of Andrei, I prepared some presentation about parenclitic networks, and I want to promise you that in more or less 30 minutes from now you understand this word parenclitic very well. So it's a method that we introduced some years ago, and the method is able to give a network representation of data for several uses, as you will see. And so I would like to and since this is a very informal workshop, I will be very informal. And please also you be very informal. That is, if you don't understand something, you just stop me. You just stop me and ask. Okay, so I start from a very important concept, which is networks provide a representation of given systems. It's a representation of natural systems. So usually in physics, we used to say that we have continuous systems which can be described by partial differential equations, turbulence, fluids, something like this. And then you have systems in which are distributed. That is, systems which are composed by many components, unitary components, and the functioning of the system is the results of the interaction of these components. So that for these kind of systems, networks provide a good representation in the sense that they give a description of these systems in terms of some mathematical tool that you can operate on. So the main idea is using network here to represent a system, to get information on this system, to try to extract information on a given system. Okay? And now I want to show you that, in fact, if you have assumed this idea of networks as representations of complex systems, you have, in fact, three classes of networks. One class that I call physical networks, another one that is called functional networks, and the third one, which will be the end of my seminar, which is called parenclitic networks. And each one applies to a different situation. So let me briefly discuss with you these first two, physical networks and functional networks, and then we will concentrate more on the new one, which is parenclitic networks. So what are physical networks? Physical networks are networks which represent those cases in which, let's say, links and nodes are very clear. What does it mean links and nodes are very clear? The system itself gives you indication on what the nodes are and what the links are. For example, social networks are physical networks in the sense that nodes are individuals, me, you, and links are some kind of relationship between these individuals. They can be family relationship, work relationships, friendship, or membership of a given community, or whatever you can imagine. But it's clear that if I have a society, I can immediately represent as a network made of many individuals and made of some relationship between these individuals. Same is another network very famous, www. www is a big, huge physical network because units are web pages. And links are just the hyperlink from one web page to the next one. So I can take the entire www and map into a gigantic networks in which each node is a particular web page and each link is a link, a direction from one web page to another. Take transportation networks. Transportation networks, and we will discuss the transportation networks. Transportation networks are networks in which nodes are cities or airports, and links are, for example, connecting ways between the cities and these airports. For air transportation, nodes are airports and links are flight. And you have 1,000 more of these things. Genetic networks, metabolic networks. I'm now going to show you a few examples of these physical networks. And especially this is a very important example because it gives a division between two different networks, homogeneous networks and heterogeneous networks. Okay? So homogeneous networks, these are two transportation networks. Road transportation and air transportation. The cities are the same. But here you have the road system connecting the city, and here you have the flight system connecting the city. And you see that there is a big difference because in the case of the road, independently on how big is a city, like take Wichita and Chicago, there are two cities of very large difference. Chicago is a big, huge city. Wichita is a very small city, but they have the same number of links. 3, 4, which is 1, 2, 3, 4. Chicago is 1, 2, 3, 4, 5. So these are homogeneous networks in the sense that independently of the node I'm picking, they have more or less the same exit route. And this is because they are planar. So if I take Moscow, I can bet that you have 5, 6 main directions to get out of Moscow. Okay? If you take St. Petersburg, the same. But if you take a very small city in Russia, again, you have 4 or 5 branches out. So these are the 4 exponential networks in the sense that if I define the degree of a network, the number of connections that a given node has with the rest of the network, and I calculate the degree distribution, I get a very nice exponential, fit. So pk is Gaussian or Poissonian, and my network has a very well-defined average degree and very little fluctuations. So this means that if I pick randomly any node here, in a blind way, I'm sure to have a degree more or less equal to k average, plus minus very little fluctuation. And these are very good because in physics, when things are Gaussian or exponential, I can do central limit theorem, I can make a lot of things on these issues. Now, as opposed to this, you have these other networks which are strongly heterogeneous. It means that, you see, you have now Chicago, which is a hub, and contains thousands of flights, and Salt Lake City, which contains only 1 or 2 connections. So here you have a huge, big, enormous difference between the degree of some nodes and the degree of some other nodes. And therefore, when you make the degree distribution of this kind of networks, you get a power law. So here's log, you see, and you have a very nice power law. And the power law for real-world networks, because you can measure from the data you have, has a slope between 2 and 3. And this is very important because if you have a slope between 2 and 3, you have the following property, that fluctuations are divergent. In which sense? You know that the average degree is the integral of k decay, and the fluctuations are integral of k squared pk decay. And this integral is between k minimum and k maximum. Okay? But now let's suppose to have the thermodynamic limit in the case of physics, so this is between 0 and plus infinity. Okay? And if pk is scaling as k to the minus gamma, this is scaling like k to minus gamma. And if gamma is smaller than 3, this goes like 1 over k, and the integral 1 over k, as you know, is infinite. So these are not only heterogeneous in the sense that there is a large difference. If I pick randomly a node, I frankly don't know where I'm going to fall. I can have a node with 1,000 connections and a node with a few connections. But they are also The most important thing here are fluctuations, are not average degree. Because if I double the size of the networks, fluctuations double. And if I triple the size of the network, fluctuation triple. So think about www, which is a growing network. Each day you have more and more web pages which are created. So this growing network, you have growing fluctuations. And then I will comment a little bit on a few things. So you have homogeneous and heterogeneous networks. And then this is www, for example. Very nice network, which is an important thing. I like very much this one. It's a study on citations. You know, so you take all the papers that have been published, and each paper is quoting some paper, and is quoted by some other paper. Okay? So what people is interested usually is how many paper quotes you know, how many papers you are quoting. And people are now crazy with this, completely crazy. So positions at the university are given on impact factor, this, that, blah, 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 blah. But if you take this, you see, you take all the, and you can plot on real data, I mean, you take the entire Web of Science, you see that this is the degree, number of citation, number of papers getting that number of citation. And if you look at the Q of the distribution, it's a perfect and very nice power law. This means that the impact factor is good if you, which is the mean, is how many citations a given paper has per average in a year, is a good indicator of how good is the journal, but not how good is the author. The author, so you can publish a paper in Nature with 0 citation because of fluctuations, and you can publish a paper in a very unknown journal with 3,000 citations. So it's very, very bad to judge people in terms of the impact factor where they're publishing. Impact factor only serves to judge the journals, how the journal is reputed, has impact in the community, but tells you nothing about the people who write actually in this journal. So that's if you want something there, but you have some property also of this kind in science authorship, in food webs, where now nodes are species, and interactions are interaction between species, for example, prey-predator issues. Again, you have this kind of properties. This is a very famous paper of 2001, who basically revolutionized epidemiology, because it was a sort of pool they made in Sweden, asking to males and females with how many partners they had sexual relationship over the last 10 years. And not how many times, how many partners, how many different partners. Obviously it was anonymous. But you see that males and females have the same trend, which means that if you want to study, for example, phenomena like epidemics, spreading of epidemics of diseases which are sexually transmitted, you need to have very heterogeneous network as a substrate of the population, and not random pairing. You need to have some non-random pairing. So this was the starting in 2001 of a new trend in epidemiology, and 1 year ago there were here people speaking about new models for epidemiology, like Pastor Satoras and Jose Mendez, and you know, this really started a new era of studies. Okay, so there are many, I could stay here months, but I mean, basically the main concept is a lot of systems in which the representation as a network is very simple and very clear. It's clear what nodes are, it's clear what links are, and you make this representation and you get some information about the system, how the system is going. Then, as opposed to physical networks, time ago people started to study functional networks, especially functional networks are studied in neuroscience, and stock market analysis. But as you will see, it's rather general method. So functional networks is a representation of a multivariate data set. The idea is I have many data here, many time series. This can be, for example, the different stocks which are quoted in a given market. So you have the time evolution of Coca-Cola and Yandex and whatever. Or they can be the signals in different position of the brain, because you're measuring electroencephalograms at different position, or magnetoencephalograms at different positions, whatever. So these are collected simultaneously. So you have, these are multivariate time series, and you don't know anything about the brain, and you don't know anything about the stock market. Otherwise, you don't do physics. And if you do, and you apply to the stock market. So the idea is, can I attempt a representation of this in a way that I can extract information on stock market or on brain? And this works with two different steps. The first step is I fix a function. That's why I call it functional network. I define a given function. It can be, for example, correlation. It can be the Pearson coefficient. It can be whatever function of two signals. Then I take pairwise these signals and I transform my multivariate series into a matrix. How? The element ij of the matrix is nothing but I take the I signal, the j signal, and measure on these two signals my function. The value is the element ij, sorry. The value is the element ij of this matrix. Okay? So for what I do, I transform this multivariate time series into a all-to-all connected weighted matrix. Because for each pair of nodes, for each pair of signals, I have the value of my function. So I get an all-to-all connected weighted matrix. Then the second step, I put a threshold and I binarize my matrix. Say all what is below a threshold put to 0, all what is above the threshold I put to 1. And so I get a network. I get a network which of course depends on the kind of threshold I'm choosing. If the threshold is high, the network will be sparse. If the threshold is too low, the network will be dense. Okay? Then I use on this network all the arsenal of graph theory, and I hope that differences, for example, between pathological cases and normal cases, be reflected in some difference between the measure that I can do on my network. So, doing the measure on my network, I can get information on the system. Now you understand that this is very, it has two elements of subjectivity. The first is, which is the function I have to choose? For each function, I have a different network. Also, are there any criteria that I have to choose a given function instead of another? All functions are allowed in principle. And second, once I've chosen the function, which is the best threshold that I have to apply for transforming my all-to-all weighted matrix into a network. So, the point number one is still unsolved, in the sense there is not a general criterion, but usually one can say, like in the previous case, depending on the typical case I'm studying, the same dynamics is giving me some suggestion about the function. I will show you later on an application of this to epilepsy. And epileptic seizures are a case of synchronization. So I use, in this case, the synchronization measure. In other cases, I can use a different function. So, in a sense, it's a sort of the literature that tells me which is the proper function that I have to adopt in a given case. Instead, for the threshold, we need a criterion. And the criterion is which is the network representation that gives me the best classification in terms of a generic problem. And if you are interested to use this kind, I suggest you to read this paper that is published in 2012, in which we gave criteria, objective criteria, for the selection of the best possible threshold. So once you have a given function, you can apply this function and obtain criteria for selecting the bestest possible threshold, so the bestest possible network representation for extracting information. The idea is mixing this kind of representation with data mining techniques, with classifiers, and finding that threshold which is maximizing the efficiency of my classifiers. That's more or less the idea. I'll give you an example. This is, I hope you don't are scared. This is a brain. It's a human brain. And this is a poor kid, because there are many kids which are suffering from epileptic seizures, and they are not responding to any kind of pharmacological treatments. And they are very, very serious. It's not like that you have one seizure each month. They have one seizure each 2 hours. So this is not life, because when you finish the seizure, you have just to prepare yourself for the next. You know what is an epileptic seizure? Did you see an epileptic person sometimes? So it means that you really have to prepare yourself. You cannot drive, you cannot do anything. So if you have one seizure each 6 months, it's a bad issue, but sometimes you can arrange your life with this. If you have a seizure each 2 hours, there's no way, you don't have a life. So these poor guys, the only solution they have is resecting a piece of brain, going to surgery and taking out a piece of brain. So this is what they do. They go in the hospital, they are anesthetized, they first open the scalp and they put on top of the brain, like here, microelectrodes, and they measure during 2 days the activity of the brain during just on the same brain. So this is the cleanest as possible data in neuroscience. For the guys who suffer, it's not good, but for us, data analysis is the best you have, because it's there is no filter, no, it's directly on top of the brain. And then the idea is that from this data, I have to analyze this data, and I have to find the place where the focus of the epilepsy starts, and I have to suggest the surgery cut there. Of course, I have to do it in a less invasive way as possible, because if I cut the entire brain, I save the guy from epilepsy, but the guy has other consequences, okay? As I told you, the epilepsy, it is a problem of synchronization. So you usually take phases, you transform your signals into phases, and phases are, in the first approximation, successive returns to maxima or minima, and you say when you have a successive return, you have a quantity which increases to pi, because you have a rotation, you know. So you can calculate phases, you can compare phases between signals, and you can use the functional network representation. Now, you see what happens. I don't go to details. This is one row of my metrics, functional metrics, and this is very interesting because, you see, this is the epileptic seizure. This is time, and for each time I take a piece of signal and I measure the evolution of my network. So this is the epileptic seizure, and as it is very well known, this corresponds to a global synchronization phenomenon. So if I measure the synchronization index, this synchronization index is very high for all the electrodes. Here I have electrodes 1, 10, 20, up to 100 electrodes. So all the piece of the brain is synchronized in phase, okay? Then, after the epileptic seizure, I should recover the normal behavior. And the normal behavior of the brain is instead non-synchronized. Because if I'm synchronized, I can do only one task. If I'm not synchronized, I can do several tasks at the same time. But you see what happens here. The level of synchronization is very low, except for few channels, for few electrodes, where it is maintained also after the end of the epileptic seizures. And actually, if you look, they have very high value of the synchronization index, and then this one are acting like a pacemaker, which is then producing a cascade of synchronization, you see, in time, which, sorry, then you have to do like this. This cascade grow, and determine the explosion of synchronization, so it determines the next epileptic seizure. So, just looking this, you can, individuate, you can individuate the focus. You can say the focus is located in this electrode area, because if I remove this, I remove the pacemaker. These electrodes, these areas of the brain are acting like a latent synchronization, which always exists, and by time they're switching on a big synchronization event. So this is a way of predicting, and indeed you can compare the predicted areas, which are the yellow ones, with actually resected area. The resected area means these are people that eventually had the surgical operation, and indeed when they coincide, you see that you have the case in which the patient was completely saved. So the patient entered with this recurrent epileptic situation and exited from the hospital without a piece of brain, but completely saved without any epileptic seizure anymore. So this is a very easy and rapid way of using functional networks for an application. Okay, so functional network is clear, physical network is clear, and now I want to introduce you the parenclitic network, which is the third class. And in order to introduce this, I have to start with the but, big but. But there are thousands and thousands of relevant cases when none of the above representation can be attempted. You cannot make a physical representation, you cannot make a functional representation. Why? Because the data have no time. The data are static. The clear case is your blood test. You go, you take the blood, you measure, and what is a blood test? It is just but the expression of such features, of some features. Glycemia that much, cholesterol that much, white cell that much, and so only once. And from this one you want to be classified. So your hope is I do the blood test, I go with this feature expression to my doctor, and my doctor has to say, I'm healthy, I'm not healthy, you have to do this, you have to do that. But the same can be genetic expression. You have thousands of genes, and you can measure if a gene is expressed or not expressed in a given moment. Or metabolic data, or functional magnetic resonance, which are usually measures in neuroscience with very, very good spatial resolution, but very bad temporal resolution. So you have one image of the brain each 2 seconds, whereas neurons have dynamics on the order of the milliseconds. So you cannot take the evolution as the real dynamics. Or, for example, evolution of national economies. Each year, each nation publishes the 60 most important macroeconomic indicator. One is the GDP, but many others are unemployment rate. And you want to, from these things, you want to say if the nation is healthy, is not healthy. You have to do some economic measure what is happening. So you have this kind of data, and you want to understand if I can attempt a network representation of this data, and what this network representation is used for, which kind of information I can extract from this. So, and now I make a parenthesis, and in order to explain what parenclitic networks are, I need to show you a few philosophers from ancient Greek. Okay? So these guys are Leucippus, Democritus, Epicurus, and finally a Latin one, which is Lucretio. Lucretio wrote the first scientific paper in the story of mankind, which is Peri Fuseus, that is the Rerum Natura. The Rerum Natura means on the nature of things. Okay? If you have time, read it, because it's fantastic. It was written 2,000 years ago, you see. He died on 50 and before Christ, and he starts saying that all the matter is done by atoms. And atoms in Greek means what you cannot cut. So the wrong guys were the chemists to call atoms the atoms, because we know that the atoms, you can cut the atoms, but he was intending the fundamental particles. And in his idea, a very important concept is that of parenclisis. So he had the idea of these atoms falling from the void and then heating one together to form molecules. And from molecules, bigger molecules, up to you. But how atoms can merge if they, for example, have parallel trajectories, because he had in mind like the drop of a ray, are parallel, they don't intersect. And so he said that during the falling there is some deviation, and parenclisis in Greek means deviation, a very strong meaning of deviation, not normal deviation. So and so it's like Maxwell devil, that sometimes this atom deviates, and this deviation allows the formation of causality formation of molecules, for Lucretio. So the idea is, let's construct a network representation which allows me to measure, to quantify the deviation of a single individual from a class. Because I have your blood test, but I have the blood test of 1,000 million other people. Okay? And so I have a class of labeled people, for example, all the people who are diabetic, all the people who are conclamated diseases. And I want to measure how different are you from this class. So parenclitic network. I want to measure how different a single individual is from a given class. So what I do is, I now go to the little bit of mathematics, but then I have a picture that tells you everything. So I suppose that I have n persons, I suppose that I have n persons, S1, Sn, each one is associated to a given class. So I have all the diabetics, all the people that suffer from this disease, all the people that suffer from this other disease, blah, blah. Then, the simple case is obviously, if I want to have a on-off classification, I have healthy, non-healthy. Okay? Control, no control. Then, I have that each of this subject is identified by a vector of P features. So this is cholesterol, this is glycemia, this is whatever. Okay? So each person is a point in RP, in this Fisher space. And I make now an ansatz, and the ansatz is that a given class corresponds to a set of constraints in the Fisher space. That is, a given class, if I project the space in all possible plane Fi, Fj of Fishers, each class corresponds to a set of functions. This is a constraint, you see, Fij equal to 0, a given function on each one of the possible planes in the Fisher space. This is my fundamental answer. So I take all my class and I learn these functions. With a normal learning algorithm like support, vector machine, whatever you want. So I imagine that from the class of all diabetic, I get all the functions, this Fij equal to 0, which individuate the class. And then a new person like me, which is unlabeled, comes, and I want to associate to this person a network which tells me how this person is different from the class. And therefore, the idea is I have, you see, my data set, healthy, 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 Fisher, Fisher, Fisher. So in this case, just to make an example, I have 3 Fishers, so it's a point in R3, okay? Then I take all possible plane, R1, R2, R1, R3, R2, R3, project. When I project the blue or the green, for example, the green class corresponds to this, I learn this function, and then when a new person comes that is the red point, I construct the following network. The nodes are the Fishers, and each link between Fisher 1 and Fisher 2 is the distance between my node and my function in that plane. So each link quantifies how I am deviating from the class, because I assume the class corresponds to a given set of constraints. How I am different from the class. And this is the way of constructing Parenclitic networks. And now let me tell you what these networks are able to tell you, why they're somehow important. First application, we took a problem which is the early diagnosis of obstructive nephropathy. This is obstructive nephropathy, the most dangerous disease for newly born for kidney. So it's an obstruction of the channel in which the kids are urinating, and part of the urine are shot back to the kidney. And so they suffer, they cry, but you don't know, because a newborn is not able to speak. So they just cry. And if you don't make a very early diagnosis, the kidney is shut down and you need to make a kidney transplant. So as a matter of fact, this is the primary cause of kidney transplant in newborns. It's a very painful and dangerous disease. So how you can treat this? You can measure the urines. You can make urine tests regularly, because the guy is urinating. So you can make urine tests, and you can measure 852 metabolites and 834 regulators on your urine. And then you have a group of 10 people which are control, and a group of 10 people which are patients. They have. So you can take all the urine blood test of these people, especially you take the urine test of the control people, and you consider them as healthy patients. So you learn all the functions that correspond to the healthy patients. And now you see, if you compare a given case with the healthy situation, if the guy is also healthy, so you take the person from the control, the corresponding network is unstructured. It's very sparse. And this is logic, because you have you are comparing a person belonging to the same class. So in this person belonging to the same class, the difference are random, randomly positioned in all possible features. So you expect to have a small difference here, a small difference there, because you are comparing the person with the same class. But if you take now a patient, you see, you get a star. And the star is very important because not only it allows you to make an early diagnosis and tell if you have the disease, but it is telling you why you have the disease, which is the feature, the most important feature that distinguishes you from the class. Look, the fact that it is a star means that in all planes where this feature is present in one of the axes, your distance is very big. Whereas there is no link between these two features, it means that in that plane you are statistically equivalent to the class. So, what the system is telling you, not only it is a classifier, in the sense that it tells you yes, no, you belong, you don't belong, but it tells you what makes you different, which is the fundamental characteristic that makes you different from the class. And we published this paper and in Physics Today, in 2011, and then we said, okay, let's go to larger class, to larger sites, because this is only 1,600 features, and we did the following problem. Problem is expression levels of genes of the Arabidopsis thaliana under osmotic stress. This is a really important problem. When 50 years ago, the problem in agriculture, the problem was biotic stress, so the animals. Now the animals are killed with chemistry, and the problems are abiotic stress. So how can I make a plant resistant to soil, to bad precipitation levels, to salinity in the soil, to these things? I want to use the desert like Israelis are doing for making plantations. So if I take a tomato and I put in that desert, the tomato dies. So I want to understand how a plant is reacting to osmotic stress. Stress which is depending on many factors, for example, salinity in the soil and so on and so forth. And I want to study this at the genetic level. Why? Because if I know the genes which are responsible of the response of the plant, I can then act on these genes, modify the plant to make the plant more resistant and to make the plant adaptable to the environment. So we took the Arabidopsis thaliana, which is, a classic plant because you know all the genoma of this plant. The genome is composed by 22,591 genes. We give a stress to this plant, a controlled laboratory stress, osmotic stress, and we measure the expression of the genes at 5 minutes, 10 minutes, 30 minutes, here is a mistake, 60 minutes, 120 minutes, and 240 minutes from the moment in which the stress is applied. Now, in each one of these, we take all the rest as normal behavior of the plant, and we compare which are the deviation at that moment with respect to what the genes are doing all the other times. So, at each moment, at 5 minutes, we take 10, 30, 60, 120, 240 as class of normal behavior. We learn from this expression, only 5 data, the functions, and we construct a parenclitic network that tells you what the plant is doing differently at 5 minutes. Then at 10 minutes I take 5, 30, 60 as normal behavior and I compare at 10 minutes. Okay? And in all cases what I see is a collection of stars. You see here, collection of stars. So what I can do, I can take the different parenclitic networks, I can measure centrality, and I can extract the centers of the stars, which are genes. I make a list of genes, and I predict that these are the genes, the most important genes of the plant with respect to the response of this stress. Why? Because are the ones who are activating strongly in different positions, make the plants different at different times with respect to the normal phenotype. So you have this list, and we went with this list to plant genomics. Plant genomics in Madrid, we say, what can you tell us about these genes? Are they known to be somehow related to osmotic stress? And the response of our plant genomics was in some cases yes, in some cases we don't know. So we say, very good, so please make an experiment now. You grow different genetically modified groups of plants. And especially what you do, you grow the normal plant. You see, this is the Arabidopsis thaliana. These are photos. And you give the stress, and after a while, you see that the plant is surviving and is growing this way. So this is the phenotype, the wild type. It is you don't do anything, and the plant is having this root length. Okay? For each one of this experiment, we have grown 100 plants, so we have making the average and the standard deviation. And then I asked them to kick one by one the genes, to block the expression of a given gene. So it's a very, very tiny perturbation because, let me tell you, we are blocking one gene and leaving 22,590 genes be free of doing whatever they want. Just you block the expression of one. Very, very tiny perturbation in the plant. And, of course, we take one by one these genes in the list. So I predict these are the most important, so I want to block each one of them. And when I block each one of them, you see, the phenotypes are indeed completely different. In this case, the plant almost died. In this case, it doesn't die, but the root is much below. And in this other case, it even overshot, so it overgrew. So really, it means that the method not only classifies, but tells you which are the genes, the most important genes, which are regulating the phenotype, I mean the expression of the plant in front of a given stress. Okay? And as a counterpart, of course, we ask the same guy to take these genes, to block these genes which are, for example, here, not the center of the star, and you get exactly the same phenotype as the normal one. So you have really a method that in a very efficient way, with only one experiment, it tells you all the most important genes. And it makes you a ranking of these genes as a function of their centralities. You can use, now we are doing the same stuff with Alzheimer. We started a very big project in Madrid with several hospitals. We are collecting, data from magnetoencephalograms and electroencephalograms and functional magnetic resonance of patients. And in this case, what is nice is that these patients are classified in different stages of the Alzheimer. So there is normal patients, controlled. There is amnesic MCI, which means amnesic mild cognitive impairment, people that they leave the keys here and they don't remember where the keys are. So they suffer from amnesic problem, or multi-domain, so they have other cognitive impairments, so not only on memory, but on different other cognitive processes. Then you have mild Alzheimer, normal Alzheimer, and each one of them you can take, learn, and then compare. So this is a large project ongoing, still now, in which you can basically, a patient tell him where you are in the different phases of the disease, what makes you different from each phases, and what you have to do, therefore, for alleviating or blocking your evolution of the disease. So in conclusion, you see, this is a method that it allows you basically to have a classifier plus identifier, I call it. And it's very important in all cases in which you have static data, data without time, that you cannot therefore use functional network representations. And potential applications, of course, I spoke about tissue and organic sample analysis, but you can imagine genetic expression levels or biomedical analysis, neuroimaging, social networks, whatever you want. So whenever you have a set of data which are static, another project that we have with a mega grant here in Russia, there is a person of Bologna who wants this mega grant. They are studying ultra-centenary people. So people which have more than 100 years old now, and they have the blood test and urine test and all the kind of tests when they were 65, 70. So they want to compare their tests with the normal 65, 70-year-old people to see if there is some indication on how is the longevity of a person. This is the object, for example, of a large mega grant in Russia involving Mikhail Ivanchenko, I don't know if you know, and a group of Bologna. Ivanchenko, I think, is from Nizhny Novgorod. But, sorry, then I give you here a few things that if you are interested. So on networks, there are three important, so to say, review. Of course, a network you can have thousands of things, but I have to do publicity to myself. So. These are things we wrote. One is in general complex networks. This is 2006. Then on multi-layer networks, 2014. And on transitions on network, 2016. But also we published a physics report on data. This is a fundamental paper in which we somehow think about how to use network analysis in connection with data. And how to merge data mining techniques with complex networks techniques, which are two communities, data mining and complex network, which are not speaking too much. But in fact, they are solving problems which are very similar. So maybe they should speak more, because one community can tell the other something that can help the other community to advance. Then parenclitic networks. There are many papers together with the physics today. The method is 2010, but you see, recently it has been applied not by us, but by other groups in the world to very, very different situations. So there is this paper in which they apply our method for survival prognosis in prostatic cancer patients. So male, they wanted to see which are the expected lifetime of these males. These other people on PLOS ONE 2017, they used methylation data for cancer identification, so it's applied to cancer identification. Then you have this paper of 2018 in which they are very nice. They use this for credit card fraud detection. You know, when you swap your credit card, the bank should decide very soon if the operation you're doing is different from the usual operation you're doing, or, and so if it is different, I have to block you because it's a potential fraud, or if it is normal, and then I let you go. Okay? This is a clear case in which parenclitic networks apply, because you just give them the differences, you quantify these differences. So it was applied to credit card fraud detection. On OncoTarget 2018, on prediction of ovarian cancer. Then, as I told you, there is partial results already on mild cognitive impairments for Alzheimer. And the last one, this year, it was used for cybersecurity issues. I don't know absolutely nothing about cybersecurity, but some people who knows decided to apply our method. So you see, it's very, very widespread, and the only common things of this is this data are static. So you have data which are static. Then, I finished. I want to make two advertisements since here we are in Russia. First advertisement is thank you, of course. It's spasiba, no? Yeah, spasiba. Thank you. And now the first advertisement is that please submit your best papers to Chaos Autos and Fractals. It's a journal of Elsevier. This year we got a tremendous impact factor. I was joking about impact factor before, but it's important for a journal. And next year we are having even better impact factor. The impact factor 2018 is larger than 3, and we expect to have something larger than 4 next year. I'm the editor-in-chief, and this year we have been converted in the top most prestigious venue in the world for statistical and nonlinear physics. So if you study something related to statistical physics, this is the best journal to submit. Please do it. And then the second one is a conference we are organizing next year in Madrid together with William Ditto and Regino Criado. And the idea is exploring the crossroads between artificial intelligence and nonlinear dynamics. Again, like I did for data, the artificial intelligent people and nonlinear dynamical people are people that I don't not speak too much. So we have tried to say, let's put together these two communities. This is the, if you want more information on the conference, is the webpage. It's a very nice webpage, and the idea is this. I mean, our brain is performing 1 trillion operations per second, and in order to power our brain, you just need a dish of pasta per day. The largest computer in the world is doing 1 over 10,000 this power, and you need half a nuclear power plant to operate this computer. So it's evident that our brain is extremely efficient. And I think that personally, the next step of artificial intelligence is just understanding how our brain is making calculations. And then constructing new software and new hardware. Because what we do now is using software on existing hardware, which are silica hardware, whereas our brain is certainly not a Boolean machine, not a Turing machine. It doesn't work with fixed architecture. It's changing and has a lot of different computation paradigm with respect to the one that allowed us to get to Siri. So Siri is not artificial intelligence. What I understand for artificial intelligence is learning how we make pattern recognition, for example, and then doing this artificially, not with. So we are trying to explore this, and there will be people working on this, but also people from Google, from Uber, from people that are really doing important and deep problems in artificial intelligence. We want to put this community together and try to discuss openly. So if you are interested, please contact me and go to the webpage. It's something that we... And then I finished. Thank you a lot.
Do you have any questions or comments right now?
When there are no comments, it is a tragedy. Yeah?
But we switched off the slides. Yes. So when you make this
Parenclitic network.
Then basically the age is the distance, right?
Mm-hmm.
Can you show back this picture?
Yeah, if I can go back, I show you back. Okay, it is not working half-half, you see. I have to...
Because I was wondering basically why do you need to plus it? Because the distance is the distance, so if you have only controls, say only healthy subjects, then unhealthy subject, like here, you can stop doing it. Yeah, here, that's the picture, yeah. Why do we need these 2 lines? Is it enough to have only healthy?
Absolutely good question, and I didn't go into all the details of the method. In general, you have M classes, like, for example, the Alzheimer case.
Yeah.
And each class corresponds to a different function. For example, here I put two classes, the green and the blue. So the green corresponds to this function, the blue corresponds to this other set of functions. The parenclitic network, in the case of a single class, is a network. In a case, more general case of M classes, is a multi-layer network. That is, this here, this link between 1 and 2 is not one scalar, it's a vector, whose first component is the distance of the point from class number 1, and second component is the distance of the point from class number 2. So you get how you are different from each of the available classes in your database.
But for each feature?
Not for each feature, for each pair of features. Because the idea is, you have now, suppose you have type 1 diabetes, type 2 diabetes, just to make something, okay? Yeah. And these are the blood tests. So all the type 1 diabetes are the green. Yeah. All the type 2 diabetes are the blue. And you are unlabeled, so you don't know if you are healthy, type 1, type 2, you don't know. So what you do is you project on all possible planes, and on each plane you learn the function that corresponds to the type 1 diabetes and the function that corresponds to type 2 diabetes. There are two different functions because the class is different. So then you have the red point, and in each of these planes the red point has many distances. It has distance from the blue line and the distance from the green line. The distance from the blue line is the first component of this vector. And the distance from the green line is the second component of this vector. So now you get a multi-layer network, a network of two layers.
It changes.
Yeah, and if you study the first layer, you tell how different you are from type 1 diabetes. Study the second layer, how different you are from type 2 diabetes.
And when you show the star, in which?
And in this case, I told you it's different, it's time evolution of things. And so here we took only one layer. Only one layer. And also here only one layer. Here only one layer because I told you, in each point I take 10, 30, 60, at 5 minutes, 10, 30, 60, 120 to 40 as the 5 elements of a class. I learned from that class. And then I compared 5 expressions of 5 minutes with this class. And I get the first parenclitic network at 5 minutes. And the star at 5 minutes tells me which are the genes which are different, which are completely different at 5 minutes with respect to all the other behavior of the planet. Then I take 10 minutes. Now at 10 minutes I have to redo the calculation of my functions. Because now I take 5 minutes, 30 minutes, 60 minutes, 120 and 240 as the normal behavior. I recalculate the class, the functions, and I take a second parenclitic network, which is how different I am at 10 minutes with respect to what I do in the all other times. And that's indeed, you see, in the list you have here, at 5 minutes, the first 5 nodes, which are the nodes with highest centrality intact in the 5 minutes parenclitic network. Then in 10 minutes parenclitic network, have different nodes. 30 minutes, 1 hour, 2 hours, 6 hours.
Can you go back?
Yes.
I just try to understand it.
Please.
But if you go back one slide, so in this picture,
this picture corresponds to one expression at one time.
Yes, but what are the axes? How do you position these points?
No, the axes are just.
So
this is not space. This is a network.
All right, but how do you draw it?
There is some normal. No, this is just a representation in a plane of the adjacency matrix of a network. Okay. And there are many visual.
Yeah, okay, that was the question.
There's no space here. No.
I understand. So basically, you give them weighted graph and then visualize it.
No. It's way you are right. The other pass is I do exactly as I do for functional network. I transform this in all-to-all weighted. Then I optimize. I take my optimal threshold, and I get the method.
Yes.
Is it possible to trace the existence of an extra factor which is not known? Because I mean, this hypothesis on the factor space and constraint space this somehow assumes that you know everything about the system. Now, with application to economics, it's clearly not the case, and therefore the saying that, say, correlation is not manifesting causal relationship is important in many applications. Did you try to plant some?
No, but this is a very interesting question. Ask another question, for example, for extending this case, is we are basically projecting in planes because we are representing our system as a network. But the constraint can be also in 3-body interactions, in 4-body interactions. So you have to do it simplices, not networks. Triangular structures and so on. So I make an answer here. Why? You can tell me, I know of a system where the fundamental is 3-body interaction. So what I have to do is not projecting in planes, but projecting in all possible R3 sub-projections and get functions and then assign constructing triangular structures with particular. So these are all extensions of the method which have not been done.
Can I ask you something related to this? And how did you choose the projection? So you take all projections because
that's another.
There is no line. And
you are right, absolutely right. And usually what we do is to be honest. So you take the data as raw data. You first pass the data on classical Fisher selection methods, which tells you which are the most important ones. So you don't consider all the Fishers, because there are many Fishers that if you consider this Fisher, in this you don't get alignment, but get a cloud.
Yeah, exactly.
You know, and so these are filtered out by regular techniques of Fisher selection. So when I say here, we have 852, 834, this is the raw data. When you pass from Fisher selection, you can end up with 100 or 200, you know?
What would be typical 100?
I don't know. 200 data, which are the relevant ones. On this one, you construct a network. So not on a subset of variables, on a subset, of Fisher. And this is the same. I don't know how many are these data, but certainly they are not 22,591. You can see by eye, between a few hundreds of them. Okay, so this is the entire Parenclitic network. So it means that, of course, you're filtering, and I'm not saying that, I'm not claiming that you get all possible information on your system. It's a way of extracting information, some information. And this is very important. For example, for the plant, usually, what they did, they really did one by one, they really one by one started to destroy, to block these genes and see experimentally if you have a variation in the, but in this case, you know, with a single expression you find 30, 40 at the same time. Whereas for them it means that they have to do 22,591 lines, transgenic lines.
But what we do is the intrinsic network, they allow significant. So at the beginning you have 100 features, then you run normal feature selections, and then you are down to 100.
I don't know how many. I don't remember exactly the data here. I should ask my collaborators, but I think if you look at here, how many points you see here? Probably 1,000.
Yeah. So, but this is of course much more than the number of the genes that you recommend to try.
No, no, of course, of course. And then you see that still these 1,000 are organized in several stars, measure stars. So look, this gene 84G1, it has, you see how many other genes?
Yeah, but did you compare this to just when you have standard feature selection, then of course you have random features from most important to least important. So if you compare the most important feature by feature selection and most important genes that you found, will it be the same?
I have no idea. This probably is something that we should track.
Discuss at this conference.
Yes.
That you organize.
Yes.
That's very interesting.
Yes, yes, it's very interesting. Okay, so we will have time for more discussions, and now let us send the speaker.